This is Audio-Visual Lecture 5, Part 2. We've been talking about the different phases of a four-stroke engine, a four-cycle engine, and we're on to stage 3, the combustion cycle. So we've compressed the fuel in the air in the top of the cylinder, and the spark plug has ignited, creating a rapid expansion of those gases. So it's not an explosion. It's not like you set off, it's not like you tossed a match into a gas can. This is a smooth, evenly burning reaction, and that rapid expansion of gases that takes place in the cylinder is what pushes the piston back down. So up here, the motion of the engine and the momentum that the engine has is pushing this cylinder up to compress the fuel and air. But in this stage right here, as this goes off, that rapid expansion is what pushes the piston back down. And this is what's called the power stroke, because this is where the power of the engine is actually coming from. Is that rapid expansion of gases is pushing the piston back down and turning the crankshaft. So now the very last cycle, get the focus here adjusted. We're very high tech around here. So now the piston is coming back up a second time, but this time note that the exhaust valve is open right here, if you can kind of see that. So now as the piston's coming back up, instead of compressing everything like it did up here because everything was closed, now that part of the cylinder is opened, as it comes up, it's going to be pushing everything out that valve. And you have a lot of burned, you have the burned fuel and air that has to be gotten rid of. So it's going to be pushing that spent fuel and air out through that exhaust valve. So step 1, you're pulling it in through the open valve. Step 2, you're compressing it and making it real hot. Step 3, you're igniting it with the spark plug, and that rapid expansion sends the piston down on the power stroke. And then as it comes up from that power stroke, it's pushing out the spent fuel and air. So that linear motion of the piston moving up and down is converted into a rotational motion about the crankshaft, which is what's turning the propeller. So those are the four cycles, of a four-stroke engine. A two-stroke engine, it combines a lot of that, but we're not so concerned about that because most aircraft are going to be four-stroke. Now, bear in mind, back to this cylinder arrangement here. That's occurring in every one of these cylinders, not at the same time, obviously. Only one cylinder is on the power stroke at a time. Only one cylinder is on the intake stroke at a time. So it's timed in such a fashion, and it depends on the engine. So when you refer to the timing, the firing cycle of an engine, for instance, we're referring to that power stroke when the fuel and air is ignited and the piston travels down. So that firing order may be, here, 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 and here, for instance. Or it may be here, then back over here, and over here. But regardless of that, only one cylinder is going to be on the power stroke at one time. So you have each one firing, one after the other in some kind of sequence, so that there's an even motion of turning that crankshaft all the time. So we're going to look a little now at how we actually get the fuel and the air mixture into that combustion chamber. So there are two ways. An older way, but one that is still widely used in aviation, is with a carburetor. And a carburetor uses a lot of Bernoulli's principle to get the fuel and air in there. So back to that intake cycle. So here's your intake valve, and the piston's on its way down and pulling fuel and air into the cylinder. It's pulling it from the carburetor. So the basic components of it, and you'll see a good picture of it on page 8 of chapter 6, figure 610. You'll see a good diagram of a carburetor there. And the basic parts of it is you have a bowl, what's called a bowl, that has fuel in it with a float, and the float rises up and down, and when the float is down here, that opens a valve that lets fuel flow into the bowl from the tank. And when the it's kind of like a toilet bowl. Um, it's exactly the same principle. When the bowl fills up with water or with gas, the float closes the valve and it stops putting fuel in there. So that supply of fuel goes into this area right here. You have a little venturi right here, and you know what happens as air is passed through a venturi, it accelerates. What's passing the air through this whole thing is the motion of the piston going down. That creates a suction in this, which is called the manifold, and that pulls fuel and air through that part. Now, think of a gas pedal or a throttle. That's what you have right here. It's a little valve that will open or close and allow more or less fuel and air to travel through there. So as you open the throttle or you push down on the gas pedal in a car, this valve, which is across here, is going to open more and more like this. The more open it is, the more fuel and air is allowed to get by. The more fuel and air that goes through, the more power you create, the faster the engine spins or the propeller spins, and so forth. So that's the basic way that, that you're getting fuel and air into the cylinder. And the text will do a little bit more as far as describing the concept of a carburetor and how that works. Now, one thing that it goes through is called carburetor icing. Now, remember that when you accelerate a fluid, you're lowering the pressure of it. So remember, with the basketball and the pump, when you're compressing the air, you're increasing the pressure and also the temperature, which is why it gets warm. When you release air, you're creating a lower pressure and you're lowering the temperature. So here's the venturi part of the carburetor. This part right here, just drawn a little bit larger here. So here's your curved wing, right? Just Bernoulli's concept of a venturi, and you're lowering the pressure. It can be 70 degrees outside, so and maybe a little humid, so there's a lot of moisture content in the air. And as air comes through, so here's where the fuel's coming in, the air coming through pulls the fuel along with it. It's accelerated through this point, and the temperature drops. So the local temperature out here may be 70 degrees, but in here you can actually drop the temperature below freezing. And when you do that, ice is going to form at that point. It's going to form first at the point of lowest pressure and therefore the lowest temperature, which is going to be right in this constriction right here. So ice is going to start to form right here, and eventually it could close off this area such that no fuel and air gets through, and then the engine quits. So that's why you have a device called carburetor heat. On most airplanes, it'll take some of the hot air from the engine and blow it on the carburetor to help lower that temperature. The other place that ice could form is where the throttle body is. So right here, this valve right here, if it's all the way closed like this, you know, the throttle's all the way back, or the gas pedal's all the way up, and, you know, no power. As you begin to add power, this is going to slowly open like this, allowing more air and fuel to get by. But now remember, when you start to close it, you're creating a restriction on either side. You're creating another venturi over here. So if there's only a little tiny opening where air and fuel can get by, you're creating the same thing as down here. You're creating a second venturi up here. You're lowering the pressure and temperature, and so ice can form on the edges of that throttle. It's going to be more likely to happen the less power that you have, because the less power means that that throttle is more and more closed, like it is in this picture. And the more and more closed it is, the more of a constricted area you're creating, and the lower the pressure you're making, the lower the temperature, the more likely for ice to form. So operationally, in a carbureted airplane, you'll usually use carburetor heat when the RPM is below a certain number, because the lower the RPM, the more closed that throttle is, and the more likely you are to create carburetor icing. Now, You're not completely off the hook with what's called fuel injection. A fuel injection system, which is described in the text as well, is kind of it's the same idea as far as controlling the mixture of air and fuel, but what it does is it puts the fuel system under pressure, and it takes the fuel to each cylinder and sprays it into that combustion chamber. It's a more efficient way of getting the fuel from the tank into the cylinder. It's more fuel efficient. You can use less of it. It vaporizes the fuel instead of just kind of squirting it in there. It's more efficient. It's more modern, and you don't have that pressure differential in a Venturi, so you don't have carburetor icing because there is no carburetor. You do still have the threat of induction icing because air has to get from the outside of the airplane to the engine. So it's got to come into the airplane at some point, and you can get ice on that point if you're flying through freezing rain or something. But that's something that's only going to occur if you're in freezing conditions. So on a 70-degree sunny afternoon, you don't have to worry about icing in a fuel-injected airplane, whereas you might in a carbureted airplane. One other thing that we'll talk about with fuel and air is the ratio that you have ideally to burn in the engine. So the ideal ratio of fuel to air is about 15 parts air to 1 part fuel, and that can be adjusted based on the engine and the conditions, but scientifically what's called the stoichiometric ratio is that 15 to 1 ratio, 15 parts air to 1 part fuel. Now it's important to note that we're not saying 15 gallons of air to 1 gallon of fuel. I mean, you could, but the units are not important. It's just 15 parts to 1 part of fuel. So that's the perfect ratio at any altitude. But what happens is, as you go up in altitude, the air becomes less dense, right? So the fuel is going to be the same that you're putting into the engine. You're always going to have a fixed amount of fuel, but the air amount is going to change based on your altitude. So you have what's called a mixture control in the cockpit, probably next to the throttle, because they go together. And what that mixture control is doing is controlling how much air and fuel you're letting into the engine. You can't control the amount of air because that's just determined by the atmosphere, but you can control the amount of fuel to adjust the ratio. So let's say that you're at sea level and you have 15 parts air, 1 part of fuel. And the fuel is the component that you can control, right? So let's say that you go up 5,000 feet, and just for easy math, let's say that now we only have 10 parts of air. But if we haven't adjusted anything on the engine, we've still got that 1 part of fuel. So now we've got 10 to 1 instead of 15 to 1. So what we're going to do is we're going to reduce the amount of fuel so that the ratio still remains the same. And you'd have to work out the math to figure out exactly what that translates down to. But we're reducing the amount of fuel to get the ratio back to that 15 to 1. And the text will explain it a little more concisely and a little more scientifically. But the main thing to remember is that with that stoichiometric ratio, we always want it to be about anywhere from 12 to 15 parts air to 1 part of fuel. And since we can't control the air based on the atmosphere, we control the fuel instead to keep that ratio balanced.